In principle, we can imagine that we could use quantum computers for designing more effective drugs.
Welcome to Nano Matters, the podcast that explores specific examples of nanotechnology. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Here with me today is Fabio Pulizzi, Editor of Nature Nanotechnology. So Fabio, we're hearing more and more about quantum information and quantum computation. What is a quantum computer and how is it different from a regular computer that we're all used to?
So in a classical computer, you have a number of single element or fundamental elements that we call bits, and each of them normally takes a value only of 0, 1. And each bit, for example, a classical way in which a bit is realized is through a very small transistor, which can be either not passing any current or passing a finite current. That would represent the two states. Now, in a quantum computer, you still have bits, which in this case are called qubits, which also assume different precise values, but they can also have a value which is a superposition between the two. So in the case of transistor, although that's not really a quantum system, but for analogy, that would be a state which is half off, half zero current, and half current passing. The most important thing is that when you have a range of qubits, they interact with each other. So in a classical computer, every information that is stored and every operation with this information that is stored is made sequentially, so one after the other. So it can be very fast, but the speed does not depend on the intrinsic nature of the element, but more on their size and on the way they interact, in the way in which they can be addressed with external means. In quantum computation, the qubits are actually acting as an ensemble, and the operation occurs in parallel, and so it can be much more efficient and much faster in certain cases.
Why do we want a quantum computer? What can it do that our normal computers can't already do?
Well, there are several types of applications that a quantum computer would be able to do faster or more efficiently. When I say faster, it could even be a situation in which a classical computer would take an infinite time to do, and a quantum computer could do in a finite time. Perhaps the most interesting is the idea that we can use quantum computer for quantum simulations. A simulation in general is used when we want to understand a system in nature, and we would study the system, and then we can, through a computer, simulate its behavior, time, for example. Now, the reality is that nature is, by default, a quantum system, especially at the very low scale. So if we want to simulate something that happens to a natural system at the very low scale, we'd have to approximate its quantum nature with a classical nature, and then whatever we come out with will only be an approximation of it. With a quantum computer, we could, in principle, use what we have to simulate a quantum system in a much more natural way, because the quantum computer follows the same laws of quantum mechanics that the system is following.
How is nanotechnology related to quantum computing?
Well, nanotechnology can offer systems that could be very good as qubits. It's as simple as that. It's a simple way in which I see it. So let's remember that a qubit is simply a system. It can be any system that can assume two fundamental values. It can be 0, 1, can be -1, 1. It can be the position of an electron in space. It can be the charge of an electron inside a small crystal. The important thing is that the systems that nanotechnology can provide, quantum dots, for example, they have the advantage they can be embedded into solid-state devices. And that makes it a lot easier to address them by electrical means, by optical means. In principle, it can also make it easier to be used in conditions that are easily accessible. For example, at temperatures which are not particularly cold, for which we have to use very sophisticated refrigerating systems or very high vacuum systems. So at the moment, the most successful results that we have in quantum computers, in fact, we can say that some quantum computers already exist. They are made with systems that require a lot of cost and a lot of effort. Probably the most valid examples are the so-called quantum computers that exist made out of superconducting qubits or of ions in vacuum. So the two require, respectively, very cold temperatures and very high vacuum. So hopefully with nanotechnology, we will be able to achieve systems that are much more accessible, even on tabletop.
So you've mentioned that there are some quantum computers in that they operate at either very low temperatures or in a vacuum, or they're specialized systems. And there's been proof of concepts and a number of announcements made by companies that they have developed quantum computing, but not in, as you mentioned, maybe on a desktop or for more general purpose. How far do you think we are from realizing quantum computing in a broader sense?
Oof, that's a very hard question to answer, because the reality is that if we make the parallel with classical computers, the first thing I think about is that we are used to documentaries or movies when we see computers several decades ago that would fill an entire room and would require a lot of attention, a lot of energy, and their power would be not even fairly comparable to devices that we have now and that we can put in our pockets. And that has taken some decades. So at the speed at which things evolve these days, one could think that it would take a lot less. But then again, quantum mechanics, quantum physics are different from classical physics. So it's very hard to know. I think an important point to consider is whether do we really need something that is used on a broader scale, for example, that we can have on our desk or in our pocket. At the moment, I can't see why we would want that. But then again, those who invented the first computers certainly were not thinking about desktop computers or laptops or iPads or iPhones. So that's not for me to tell.
So where do you think this technology will have the most significant impact?
From what I can see now, and particularly from what I hear experts in the field saying, I have to go back to quantum simulation. One of the things that people say often is that in principle, we can imagine that we could use quantum computers for designing more effective drugs. That is one simple example, in the sense that if we think about drugs as big molecules, which are governed by quantum mechanics and quantum physics, having a quantum computer that allows us to simulate the properties of molecules at the larger scale than just 2 or 3 would certainly help us in creating drugs that could be more effective, that would have properties that we desire.
So Fabio, thank you so much for joining us today. I think that's been a great discussion of quantum computing, what it is and why it's important. Do you have any closing thoughts that you'd like to share with our listeners?
Well, maybe one thing that I'd like to say is that when we think about quantum computing, particularly quantum information, but quantum computing particularly, the first thing we think about is the final goal, which is creating this quantum computer. And that's great, that's fine. But what I think is the greatest thing is that drive towards creating an actual product, in fact, gives us the opportunity to look at the fundamentals of quantum mechanics. Yes, it would be great if one day we have a very efficient quantum computer, but what we will learn on the way will perhaps reveal to be more important than the final product.